We've checked out our results of our experiment tracking with TensorBoard. Now let's do the fun part of importing in. So load in the best model and make some predictions with it. So just like we did in the last section, PyTorch transfer learning, I'll give you a little challenge if you'd like to pause the video here. So we're going to make some predictions on images from the test set. So if you'd like to give that a go with our best performing model, load it in and then follow this section here and see if you can make some predictions on images from the test set. And let me just clean up this. There's our results on the tensorboard.dev. Just going to get out of that. So we've got some space up here. I believe that is all we need for now. Wonderful. So we've decided that our best model was EfficientNet B2, Pizza Steak Sushi 20%, and we can come up here and get its path name. So it's this one here, models/07_FNetB2 data 20% 10 epochs.pth. Ooh, that's a bit of a mouthful. So this is our best model file path. Wonderful. So we can now write some code to load this in. So set up best model file path and we'll go best model path equals, and we'll put that into a string. Now we need to instantiate a new instance of FNet B2 to load in because this is a state dictionary. Our save model function saves the model state dictionary. So we need to create a new instance of FNet B2 to load in the saved state dict. So let's go best model equals create FNet B2, and then we need to load the saved best model state dictionary. So if we go best model.load state dict, we've seen this a few times across the course. We're going to go torch.load best model path. So we've got our best model creating a new FNet B2 using the function that we created above. We've got best model path here, and we're going to say, hey, for the best model, let's load in the save state dictionary that's here, and we'll do that using torch.load this file path. So let's try that out. We created a new FNet B2 model and all the keys are matched successfully. Beautiful. Now, there's only really one way to test this, and that's to make some predictions. But before we do that, we're going to check the model file size. So this is a sound check to make sure, remember, what's our goal? Our goal, this model is performing at 95% test accuracy, or so it says, numbers on a page. Our goal is to create a Food Vision mini model that performs well enough and is able to run on a mobile device / web browser. So very similar to what I'm doing here for Nutrify.app. This model runs directly in the browser. So because Food Vision Mini identifies different photos of food, and where do people take photos? On their phones. If we had infinite compute, we could maybe do a model that's much bigger, but phones and browsers are limited in compute. So from pathlib, import path, we're going to see how big the model file size is. And we can do that programmatically. Size in bytes. We'll get it in bytes first, then convert it to megabytes. Because that's pretty understandable, right? So we want FNet B2 model size, and I'm going to go path, and then I'm going to go best model path. So we're using the path module here, and then we can get some statistics from that using the stat method, and then we can get the stat size. So the stat size attribute, that's going to return the size in bytes, and then I'm going to convert it to megabytes by dividing it by the multiplier of 1024 times 1024, because there's 1 million and something or other bytes in a megabyte. So let's go here. My conversion might not be exact, but it gives you an estimate of how big your model is. So EfficientNet B2 feature extractor model size is FNet B2 model size MB. Let's see if this works. Oh, that's pretty good. 29 megabytes. Now, what is our limitation? Well, that's a tough question, right? We don't want it to be gigabytes in size. We also don't want it to be too small, otherwise its performance might be degraded. So I think this is a good value to go forward with for now, and we can check it out if it works or not later on in the course in another section that I'm not going to give away too many spoilers now, where we try to do something with our model which is very much like what we've spoken about here. So let's keep going. We're now trying to plot or make some predictions using our best trained feature extractor model on the test data set. So how about we do that? We're going to import a function to do this, to make predictions on images and plot them. So you might have seen this, you might not have, but in this section, section 6, we did create a function here, pred and plot image. What I've done with this function is, rather than us rewriting it over and over again, I've been a bit sneaky here and put it into going modular, and we've got a function here or a file here called predictions.py now. And all I've done is I've put this function into here. So that way we can just import pred and plot image from predictions.py and use it. So you see, the whole point of going modular is to, if you're writing code over and over again, you might as well put it in a Python module. So predictions, import pred and plot image. So we just saved how many lines of code that is, like 30 or so. 80 lines. We just saved 80 lines of code or thereabouts with one line of code. So let's get a random list of path names, of 3 image path names from the test data set. You know how much I love randomness. Let's go import random num images to plot. I'm going to set this equal to 3. We just want 3 random test images or the paths to test images, because that's what pred and plot image takes in. It takes in an image path and a trained model, and we'll make predictions on that image and plot that image as well. So test image path list. We're going to get a list of path, and then I'm going to put in data. Let's get the 20%. 20% path / test. We'll qualitatively evaluate our model on the, I believe this is star, on the 20% test data set. And then we'll get a test image path sample. So we only want 3 of these. Random.sample, and I'm going to sample the population that is the test image path list, and the number of samples I want to get is num images to plot. And then here is where we can loop through this test image path sample. So for image path in test image path sample, what are we going to do? We're going to call our pred and plot image function, and the model is going to be equal to the best model, which we've instantiated up here to load the state dictionary. And then we're going to set in the image path is going to be equal to the current image path within the loop. Then the class names is going to be our class names variable that's followed us through most of the course. And then we got an image size here, which is 224, 224. We don't need to set that, that's the default, but we will anyway. Are you ready? We're going to use our best performing model so far to predict on images it has never seen from the data 20% path test set. In 3, 2, 1, let's go. Oh, I missed the key there. I'm so excited. Pizza, oh, that should be steak, so that's wrong. Sushi, that's correct. That's steak. Wonderful, that's looking pretty good. Let's go again. It is 95% accuracy on the data 10% test set, so there are going to be some mistakes. That's steak. Steak, sushi, well done. What do we have? We'll do one more after this. Pizza, beautiful. Steak, sushi, and one more for good luck. Pizza, steak, and pizza. Oh, our model is doing pretty darn good. So what was that? About 12 images and it got 1 wrong? What the hell? One more. We'll finish it off. Sushi, steak, sushi. Holy moly, our model is doing very well. So that is very exciting. Our best performing model is in fact, doing quite well. Let's now finish it off by making a prediction on our own custom image. So images that aren't even in the test set. Now, we've done this before. I'm going to issue you the challenge to give it a go yourself. If you go to the repo, we're going to use the old faithful Pizza Dad image. So if you want to download this into our notebook and make a prediction with our model, you could use this function here and see how our best performing model goes so far on it. I'll see you in the next video. Let's see if our model can correctly classify Pizza Dad.